All right, ladies, so this is one video. I'm gonna get started because I don't want to waste time. I'm gonna try to keep it to 2 videos, and I'm gonna try to keep it under 15 minutes each. So let's get started. We left off in class, so I just want to conclude section 10.7 before moving on to 11.1. That's going to be the majority of the notes. But here, I gave you all this theorem in class. And so I just want to make sure we go back over it, and I want to give you just 2 examples on how to apply this theorem. So it says if f of x is represented by a power series centered at C, so you know what a power series is, in an interval, we see where we have this interval convergence and R is our radius of convergence with R being greater than 0, then the power series is the Taylor series at that given center, okay? And what does that theorem mean? So how can that theorem help us? Well, let's look at this example. So here it says find the Maclaurin series and find the interval on which the expansion is valid. Because remember, when we set up, so recall, we said that the series x to the n goes from 0 to infinity. It's equal to 1 over 1 minus x when what? Similar to geometric, right? We sort of mimic geometric when the absolute value of x is less than 1. And I had you all take a function and create a power series expansion on it. And so what this is saying is that if you find, basically that theorem is telling us, if you find a power series expansion and state what interval of convergence it's on, for which is valid, as long as R, going back here, centered at some C with R being greater than 0, then it is your power series, okay? So this question is saying find the Maclaurin series. So remember what we've been doing in class is taking the derivatives, right? So this actually is a nice, because if we know how to take this function and do the power series expansion, we don't have to keep taking derivatives and look for a pattern. So that's the impact and the power of that theorem. So let's look at this one. I don't like yellow. All right, so we have we know this information here. We have 1 over 1 minus 2x. You all should know by now how to write this as a power series. This will be written as 2x to the n, right? Which n goes from 0 to infinity. And this is 2 to the n, x to the n. Now the purpose and the real meaning behind separating is the fact that you want to get that x sort of to the n, or x, it could be x minus 2, x plus 1, whatever to the n. You want to get that isolated because this tells you what your center will be, right? And this center here is what? 0, right? And we're asked to find the Maclaurin series, so that means the center is 0. And when is this valid? Well, when the absolute value of 2x is what? Less than 1. And then that's when the absolute value of x is less than 1/2. Okay. And so it's valid. That's the valid, what we call, this is our valid interval. So on that interval, this is the Maclaurin series, which of course we know Maclaurin is a type of Taylor series centered at 0. And we've answered the question. So we don't have to remember the process in general. And of course, if you just want to have some fun and play around with derivatives, you can take that, then evaluate it at 0, right? And then take double prime, and then evaluate that at 0, and keep going on and with that table. And what you're going to end up with is this here. Well, I guess I should say this is on an interval where it's valid because we're using the power series expansion, right? So it's only valid on this interval. This 1 over 1 minus 2x is equal to this Maclaurin series here, this power series, which is now our Maclaurin series by that theorem, okay? Okay, so here we have to find the Taylor series for this function centered at -1 and state which interval for which is valid. This one is a little more involved. And why is that? Well, correct, you guessed it. Because our center needs to be -1. Whereas in this standard form here, the center is 0, right? So if we want a center equal to -1, then that means, I'm working sort of backwards now. That means this would have to be x plus 1, right? Because that would represent a center of -1 when we first started talking about power series. Well, how would that impact that 1 minus x? So it'll look like 1 minus x plus 1, right? Because it's sort of just this substitution here and here. So we have that form, and this will be valid now when x plus 1 is less than 1. And so we would have to take it out the absolute value and add -1 everywhere. And so this will be when x is between 0 and 2, it's going to be valid. That's how we want to think about it. Now, in our problem, we're starting off with, what are we starting off with? 1 over 3x minus 2. Well, first let's rewrite it because we're used to the x being here, right? So let's rewrite this. We'll rewrite this as 1 over 2 let me do this right. It will be -2, right? -2 plus 3x. And so again, our goal, keep in mind our goal, we have to get somewhere in here x plus 1, right? Because that's going to represent our center. Remember, we know that has to be a 1, right? So if we, and why do I feel like I'm doing this? Am I doing this differently? Yes, I think I'm doing this differently for my notes, but that's okay. Let's see what happens. All right, so if we factor out a -2, we'll have 1 minus 3/2 x. If I did that, that's -2, and then that's going to be plus 3x, yes? And so now, this is 1 over -2 times, well, we can write it as, if we want to see this better, we can write this as -1/2 times 1 over 1 minus 3/2 x. And if we just needed a center of 0, if our center was 0, then we would be pretty much done because we would just plug that in. But our center needs to be 1. Okay, so our center needs to be 1. Okay, so we want this x1. So we actually have to do a little bit of work here, some algebra, something along the lines of completing the square, or makes you think about completing the square. So I want to start on a fresh new sheet of paper or board. All right, so let's start. So we have 1 over 3x minus 2, right? First, I want to rewrite that. I think that's what I did on the last slide. All right. Now, remember, we want this to be a 1, right? So I'm going to rewrite this, or I'm going to force factor out a -2, and that'll give us 1 minus 3/2 x. I'm going to rewrite this as -1/2 times 1 over 1 minus 3/2 x. Okay. And here's where it gets very fun, but maybe a little tricky for some of you all. All right. Now, I know, so I have my -1/2 out there. I know that I want that center to be x plus 1, right? So I'm going to write -3/2. I'm going to put in x plus 1 because I know I want that to be my center. But because I don't want to change this expression, if you remember, like with completing the square, you have to balance. So what did we bring in? So because we started here, but we brought in this plus 1, which was really, if we distribute this 3/2 to 1, we really brought in a -3/2. So to balance that off, to make that a 0, to make sure we bring it in 0 and anything plus 0 is going to be itself, we add 3/2 here. Okay. Go back over and see if that makes sense. And you can check the algebra to make sure. But we don't want to change anything, right? And so really, instead of me putting arrows, I put the arrows just so you know I'm going on the next page. But I really should just put equal signs here because these are still all equal. All right. Now let's put the constants together. So we have -1/2 times 1 plus 3/2 minus 3/2 x plus 1. And I'm going to put this sort of in a bracket so you can see that's what we're going to put. Once we balance things out, that's sort of what we're going to plug in, although it might change. Let's see. Keep going. So this is -1/2 times 1 over 5/2 minus 3/2 x plus 1. It's all in the bracket. Now we still need to make that a 1, right? So now we have our center as -1, but now we have a constant other than 1 here. So we need to force factor that out again. So -1, and I'm going to simplify this. So I want you to check my work, but because of time, I'm going to simplify this. And what you should end up getting is this. Actually, once you simplify, you should end up with -1/5 times 1 over 1 minus 3/5 times x plus 1. That becomes -1/5 times the series. Now we can plug in 3/5 x plus 1 all raised to the n, which is equal to, I'm actually just going to give the final answer. So again, I'm skipping steps. Don't skip steps in your notes because I want to make sure you understand how we got that. But your final answer is actually going to be this. From n equals 0 to infinity of -3, and that negative is not in parentheses, it's just -3 to the n over 5 to the n plus 1 times x plus 1 to the n. And this is valid for the interval -8/3, 2/3. All right, so I want you to check to make sure that's correct. I'm going to stop this video here because I'm going to start 11.1. I'll try to get it done in one video. If not, you might have 3 videos total to watch. But you have time since Monday we will not have class. Okay.